As we begin our journey through the world of organic chemistry, one of the first things that we need to understand in order to build a foundation for us to explore complex molecules is we need to understand how different atoms bond together. And the two types of bonds that we're going to focus on are the ionic bonds and the covalent bonds, which you've probably seen these topics before when you were taking general chemistry or similar courses. And what we're going to do is try to highlight how these bonds come into play within the context of organic molecules, that is, molecules that contain carbon, and what features of these bonds you need to be most familiar with in order to be successful at understanding organic chemistry. So much like with a lot of the different concepts from chapter 1, this topic is going to build some foundation work for us to later build upon understanding the basic principles of organic chemistry. When we talk about different types of bonds, the objective of atoms engaging in chemical bonds, be they ionic bonds or covalent bonds, is that they aim to fill their outer valence shell so that achieves the highest stability possible. In most cases, most of the atoms we're going to encounter will undergo chemical reactions to form bonds to achieve a full outer shell that has 8 valence electrons. In other words, fulfilling the octet rule, which you should be familiar with from your general chemistry background. So when we talk about bonds forming, we're generally going to be aiming at fulfilling the octet rule. And as a reminder here, it is best when you're looking at and exploring these videos to have your notebook out and be taking notes as you go through, just like you would in a normal class. That's how you're going to get the most out of this as possible, is by engaging as many senses as possible, meaning watching this, listening to the audio, and writing things down. That will be the best strategy for mastering the materials from these videos. Also, using the accompanying worksheets to reinforce the concepts is an excellent idea as well as we go through our organic chemistry journey here. So the octet rule says that most atoms, such as the ones we're going to deal with primarily in organic chemistry, such as carbon, nitrogen, and oxygen, all obey the octet rule, and they're going to react with the final outcome being to give relatively stable compounds that have 8 valence electrons. So we aim for 8 valence electrons that are going to be associated with the common atoms that we will deal with here in organic chemistry: carbon, oxygen, nitrogen, and typically, most of the time, for organic molecules, sulfur is going to follow the octet rule as well. Sulfur is one of those atoms that can, in some cases, exceed the octet rule. For example, if you think of the Lewis structure of sulfuric acid, for example, from your general chemistry class, in the structure of sulfuric acid, you can see that sulfur is able to exceed the octet rule. In most cases here, when we're talking about sulfur in the context of organic molecules, we're going to be seeing that the sulfur atom follows the octet rule. And certainly carbon, oxygen, and nitrogen, we think of those atoms within stable molecules, are going to follow the octet rule. So that's something that we're going to be looking for as we think about why different atoms engage in chemical bonds. When engaging in chemical bonds, you do need to keep in mind that hydrogen, a common atom that we will see with respect to organic molecules, does not follow the octet rule. Hydrogen has a complete valence shell with only 2 electrons, so you'll need to keep that in mind, that you absolutely need to have just 2 electrons associated with each hydrogen atom, because hydrogen is going to have a full valence with 2 electrons. In order to fill the required valence, that being the octet for carbon, oxygen, nitrogen, and a variety of other atoms, or 2 electron valence for hydrogen, the atoms are going to engage in ionic and covalent bonds in order to accomplish that. What we're going to talk about is how we determine what type of bond a particular atom is engaged in when we see that an atom has formed a chemical bond with another atom. And we're going to go through some of the criterion guidelines for determining whether a bond will be ionic versus covalent. So let's take a look first at the general definitions of an ionic bond versus a covalent bond here. When we talk about an ionic bond, one of our 2 main types of bonds, we're referring to a bond in which the electrons are not shared between the 2 atoms, but instead they are transferred entirely from one atom to another. So one atom is losing electrons as the other one gains electrons, and then they're going to be involved in an ionic bond. So an ionic bond formation involves the electron transfer from one atom to another. And the goal of this, again, is to satisfy having a full valence shell of 8 electrons if it's an atom that follows the octet rule. So we're looking at the transfer of electrons from one atom to another. For example, one that we're hopefully familiar with from general chemistry already is sodium. Starts off with 1 electron, valence shell. Chlorine has 7. And so what happens here is that 1 electron gets transferred from the sodium to the chlorine. So this 1 electron comes over, and I'm using an arrow to show that electron transfer. You'll see the starting point of that blue arrow is on the electron that's associated with the sodium. And the end point, that is the arrowhead right here, that single arrowhead denotes that that electron is moving over to become associated with the chlorine atom. And so as a result, that 1 valence electron that was in the outer shell of sodium is now associated with chlorine. The sodium, then, since it's lost that electron, would have a +1 charge. And the chlorine, since it has gained that electron, would end up having a -1 formal charge. So that's going to be the gist of ionic bonds. And the thing that you will notice about ionic bonds is that once the ionic bond has formed, generally, you're going to see that the atoms have complete formal charges. And we consider an ionic bond to be a situation where the electrons are completely transferred. They're not being shared between the 2 atoms. The interaction between the sodium and the chloride there would be an electrostatic interaction, resulting from the positively charged sodium and the negatively charged chlorine. A covalent bond, on the other hand, is going to be a situation where the electrons are being shared between the 2 atoms. So we talk about a covalent bond. We're looking at a situation where 2 electrons are being shared between 2 atoms in order to fulfill the required valence or the octet rule for each of those 2 atoms. So it's going to be electrons shared between 2 atoms here. And in the covalent bond, for example, we could do the simplest organic molecule possible, which is methane, CH4. You will see that we have a total of 4 covalent bonds connecting our carbon atom to our hydrogen atom here, 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 and here. We show those covalent bonds with single lines there, and each bond denotes that there are 2 electrons, and that line indicates the 2 electrons are being shared between the carbon and hydrogen. Since carbon has 4 covalent bonds coming to it, and there's 2 electrons per bond, that's a total of 8 electrons, meaning that carbon has filled its valence. And it's going to be a very, very common situation. We'll see that carbon will have 4 bonds associated with it. That is going to be how carbon typically fills its octets to create the most stable types of molecules that it possibly can. The hydrogen here, you will see, also has completed its valence because it has the 2 electrons associated with that covalent bond. Remember that 2 electrons constitutes the complete valence shell for a hydrogen atom. So how do we go about deciding if a bond between 2 atoms will be a covalent bond or an ionic bond? How do we know whether the electrons are going to be completely transferred from one atom to another, in other words, or whether the 2 electrons will be shared between 2 atoms? The way that we tell whether the bond is going to be ionic or covalent is look at the difference in electronegativity between the 2 atoms that are engaging in the bond. Typically, if the electronegativity difference is very large, we describe the bond as being an ionic bond. If the difference in electronegativity between the 2 atoms is relatively small, we describe the bond as being a covalent bond. So where's the cutoff line that we put between a covalent bond and an ionic bond? In other words, how large does the electronegativity difference need to be between 2 atoms for the bond to be referred to as an ionic bond rather than a covalent bond? Typically, the cutoff point between an ionic bond versus a covalent bond is a difference in electronegativity of 1.9. So we're answering the question of here, how to determine or how to assign if a bond is a covalent bond or an ionic bond. So what we're going to do is we will look at the periodic table and compare the electronegativities of the two atoms that are bonding together. You will always, for purposes of exams, quizzes, and whatever else, have access to a periodic table. That periodic table is posted on the Canvas webpage for the course, and that periodic table has embedded within it information on the electronegativities of each atom in the periodic table. And so typically we say that our cutoff line here is if the electronegativity difference is greater than or equal to 1.9, we describe the bond as ionic. On the other hand, a difference of less than 1.9 makes the bond described as covalent. And yes, there is a relatively gray zone here, where when the electronegativity difference is approaching 1.9, you're getting into a zone where the bond is becoming very, very, very polarized, almost to the extent of being able to be described as an ionic bond. So it's not a totally black and white situation here. We're at exactly an electronegativity difference of 1.9. The bond transitions from being covalent to being ionic. Instead, it's more of a gradient, and there is that gray area in between where the bond is somewhere in the zone between being described really as an ionic bond or as a covalent bond. And we're going to see several situations where that sort of scenario impacts the way that molecules will react. So we have to keep a little bit of an open mind here that we classify bonds as ionic and covalent, but it's really a spectrum between those two extreme ends where we can have bonds that are very, very, very polarized to the point that they're almost ionic bonds, but perhaps still meet these criteria of being covalent bonds. So let's take a look at a couple of examples of chemical bonds that we might see and try to determine whether the bond would be an ionic bond or a covalent bond. And let's just start with the example of a carbon-hydrogen bond, because we will very commonly be running into carbon-hydrogen bonds. Perhaps those are probably going to be the most common types of bonds that you will run into in organic chemistry. So we're looking at a carbon-hydrogen bond here, and I've shown it so far here as a covalent bond showing that line between the two atoms. But we're going to ask the question of, is that bond really a covalent bond or an ionic bond? To address that, what we do is look at the electronegativity of each of the two atoms that are engaging in that covalent bond. So now would be a good time to pause and get out your periodic table if you haven't already got that out. It is available on Canvas in the Files section. And the periodic table available in Canvas is the same periodic table that you will be provided on every exam in this class. You will also, of course, have access to that when you're taking the quizzes. And it's a good study tool as well. So if you take a look at that periodic table, and if you go down to the lower left corner, there is a chart or a key to what is represented within the periodic table. And if you look at the left-hand side of that, and you go down to the fifth line, it's going to say electronegativity. So the electronegativity value is what you're going to find on the fifth line for each of the elements. So if we take a look at the electronegativity value for carbon, you're going to see that the electronegativity value for a carbon atom is going to be equal to, looking at the periodic table, carbon is at electronegativity 2.55. Let's go ahead and fill that in for carbon. Hydrogen, on the other hand, if we look at the electronegativity of that, going down to the fifth line on the left-hand side of that entry in the periodic table, has electronegativity of 2.20. So what we do is we subtract those two values from one another, 2.55 minus 2.20. And by the way, in this class, you will not need your calculator for anything. It won't be necessary for exams or quizzes because any of the math that you're doing here should be math that you can do in your head, or at least approximate in your head closely enough that you can get the correct answer for the types of questions that we're looking at. In the vast majority of cases, we're going to be looking at things rather qualitatively rather than necessarily rigorously quantitatively. So the electronegativity difference between these two atoms is only 0.35. Indicating to us that the bond between these two atoms must be a covalent bond, a bond where those two electrons are being shared between the two atoms. So let's do another example of looking at whether a bond is an ionic bond or a covalent bond. Let's take a look at the example of, we'll say, carbon with sodium. So carbon-sodium bond. We'll take a look at the electronegativity difference between those two atoms to assess whether that bond we expect to be a covalent bond or an ionic bond. The electronegativity of carbon is still 2.55, as we saw above. Electronegativity of sodium, we'll go into the periodic table and look for that electronegativity value. Going down to the fifth line on that left-hand side of the periodic table that you have available on Canvas, we see that the electronegativity value of a sodium atom is 0.93. So we go ahead and do the math to subtract those two values. 2.55 minus 0.93, give you a second to do that. And that means the electronegativity difference between those two atoms is going to be 1.62. So if the electronegativity difference is 1.62, that's going to also classify this bond as a covalent bond. What you're going to find in general is, due to the fact that carbon is situated relatively close to the center of the periodic table, that when you look at the electronegativity difference between carbon and other atoms, we are generally going to see that the bond between carbon and other atoms is a covalent bond. So it's typically going to be covalent bonds that we are dealing with here in the organic chemistry course, because of the fact that carbon is there relatively at an intermediate electronegativity. And as a result, most of the bonds are going to be classified as covalent bonds rather than as ionic bonds. So with that, what we need to do is discuss, within the realm of covalent bonds, when we have two atoms that have different electronegativities, are the electrons going to be evenly shared, or are they going to be disproportionately shared, and one of the two atoms will have greater than its fair share of the electrons? In other words, will one of the atoms get the lion's share of the electrons of that covalent bond? The answer is yes, absolutely. The more electronegative atom is the more electron-hungry atom, and it is going to take a disproportionate share of the electrons from that covalent bond to make the bond polarized. In the next segment, what we're going to look at is how we can evaluate the polarization of these covalent bonds. When we see that there's a difference in electronegativity, how can we go about assigning which atom is going to be positively polarized and which is going to be negatively polarized? In other words, which one takes more than its fair share of electrons versus which one takes less than the equal share of electrons.